Okay. Yeah. I'll just restart then. So today we'll be discussing about CLIP, and I'll be just presenting what are the things that I've learned from this paper in the last couple of days. I have not prepared any formal notes or anything, but these are basically my own personal notes that I'll be describing from. Uh, Also, we will not be going through the entire paper like line by line. I hope that people have more Q&A so that we can actually make it more interactive. What I'll do is just summarize the overall observation this paper actually points out, and as well as how it helps us going forward. So the entire paper can be summarized by in these two images. One is this one, and the other one is this particular code section, which is actually from the paper itself, which is at the towards the bottom. Why does this summarizes the entire paper? Is that so? The clip is not an image generation or a text generation model. It's more of a suggestion. It's an architecture pattern. You can think of it like this. The name itself comes from, so the clip, the acronym comes from contrastive learning of image to text or text to image. P standing for pre-training. What does this means is that what Clips wants to say is, imagine you already have your entire, no, not, you don't have to imagine, you already have a data set, right, with images and text. Now this is our internet effectively. The question is, how can we leverage this information, right, to actually annotate all our images in such a way where the embeddings or the model itself is quite useful. Like you can do classification tasks, you can do zero shot learning or any of the else above, right? Clip says that you don't need label data set, because if you think about all the approaches, any convolution neural network that you learn, any kind of image classification, like basically image processing, whenever you learn them, you always have a setup where you have a model, right? And you have this labels, and then you have your input, right? And this is always a setup, and any loss function you give, right? Yeah, this loss function is trying to map this f of input with this labels, right? And this is the setup that we have learned till now. What Clip says that we don't need this, because it's, first of all, it's not possible that every time you like want some new task, some new classification task to be created, you go and do a human annotation. It's simply not feasible, right? Like Nikhil just mentioned, right, he many times have some like very specific kind of use cases for his own optimization or other stuff that he tries to design, and in those cases it's not possible for him to always get the infra or the model trained out, or even the data as well. Like you're not going to get annotated data. Yesterday I was discussing with someone, like I consult every now and then, and they were trying to actually detect, basically the use case was that you have basically rucksacks, right? Sacks of grain, and they want to actually detect how many such kind of rucksacks are getting unloaded and offloaded to the warehouse. So in such case, how are you going to get annotated data for that? So that's the question you need to ask yourself, that what do I do when I don't have annotated data? And that's what Clip is trying to answer. And the answer is this particular piece of code and this image. So we'll quickly dive into what this image really tells us, right? Piece by piece. One is, you have a text encoder. Now, if we go by the code, which we will do by the end of it, there is no recommendation of which encoder you would like to use. You can use any encoder that you want, right? Be it BERT, be it GPT, whichever you are fine with. As long as there is a text encoding and it's reasonably able to give a good embedding to you, it should be fine. That's one. And the other one is the image encoder. Again, there is no opinion on what the image encoder should be. It can be a ResNet, a residual network. It can be a DenseNet. It can be VGG, whatever you want to dream up, or a vision transformer, right? I'll just pause here and ask any doubts, any questions anybody have, like before I go on to like do a deep dive into the model. Does anybody have any questions on the motivation?
I guess you can go ahead. Okay.
I think okay. Okay, great. Okay. Yeah. So we'll do a deep dive on the model. So basically, I already described. So you have your text encoder and you have your image encoder. Now, what we're going to do is that okay, we have bunch of embeddings created out of the images. So during training, you're always going to create a mini batch of your data set, right? So you have your model. Suppose this is your image encoder, and whenever you're going to give the images, you're going to give a mini batch of it. Suppose let's say of size B, right? And you're going to get an output of out of your image encoder something of size batch B against a vector size of maybe let's say M, right? And in case of your text encoder, right, you're also going to get maybe you can do a batch size of B or maybe you can do a batch size of C. It doesn't matter. So let's just keep it B for simplicity, right? So you have bunch of text annotated documentations, right? And you also get some embeddings out of them, and you're going to get a size of maybe B by M, right? So this particular code, if we take a look here, is exactly that, right? We take a normalization and then we do a dot product of them, and then we basically apply a cross entropy loss on top of it. The idea is what we're trying to do here is basically create a contrastive loss against each of the correct sample of images against both the correct annotation as well as the wrong annotation and as well as the inverse. So imagine if you have like 10 sample of image and text. So within this 10 sample, you're going to take all these, sorry, you're going to take all the 10 samples here. So you have your image, you have your text, and you kind of like compute this metric uh, of that cross entropy applied one against all of them, right? So that's why the hence this large matrix. So if, your image I is like mapped with Ti, image 2 is mapped with T2, and throw all, and so on and so forth, right? And then you just apply a cross entropy loss, and that's effectively your contrastive loss. You might notice one thing, and this is something like if you start going to the code might confuse you, is that why we are doing it twice. So you can see you have your loss I and loss T. So the idea is that whenever you're calculating cross entropy, you're actually calculating the cross entropy against the entire row, right? So you calculate it against the entire row once for each of the rows of images, and then you do the exact inverse task. You say for this given text, which image is the most closest to it. So you also calculate your cross entropy like this as well. You once both of these are calculated, you can then add them, and that's your final loss. Yeah. Does that make sense? Because otherwise, I'll just repeat it.
But in your case, the horizontal oval you drew was loss I and the vertical one was loss T, right?
Mm-hmm. Sorry, I
And in
didn't get that.
paper, so you circled the first row and that was loss I, and then you circled the first column, I mean the last column and that was loss T.
Uh, when you say the last row, as in because we're technically calculating it for all of them, right?
Yeah, but why are they doing loss equals loss I plus loss T?
Oh, yeah, because okay, yeah, that's okay. So this is more of a how do I put it? It's more of like it's just easier to calculate the gradient like this. So if you kind of like take loss I and loss j separately, and then try to do a backward pass, you'll have to clear that gradients and then do it again. You can do it separately as well. That's perfectly fine. But the motivation for having both of them is basically like you try to ground the images which are in the one image which is relevant to the current text prompt, and you do the inverse task as well, that which text prompt is relevant to this image. The reason for adding them up is just pure simply like you can do it separately, but then
Okay,
you're
okay,
going
I
to
get
have
it.
to manage
Yeah,
that. Yeah.
okay.
Yeah.
Yeah, one question.
Yeah.
Uh, so your target is the diagonal elements. So for example,
Hmm.
I1 and T1 is my first, and the off diagonals are the ones where I want. a low score, low
Yep.
quotient functionality, right?
Yes.
All right.
Yep. Okay.
Also, you have logic equals that np dot of IE blah 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 and then np dot x of t, right? What is t?
Which one? Which line you're saying?
Okay, it's the temperature parameter. Okay. Hmm.
You mean this or the one above?
Yeah, yeah, that one.
That's the one, right?
Yeah.
Oh, okay. Oh, this is okay. Yeah, yeah, yeah. Yeah, cosine similarity and p dot. So you have your dot product, and then you have a multiplication with the exponential, which is the t here,
It's the
which is the
You
t
have
temperature.
here.
mentioned that it's
Ah,
temperature, so maybe there's some kind of decay or something.
probably I'll have to check in the implementation again because again probably it might have been done for numerical stability because the contrastive loss itself doesn't have any motivation of adding this particular one.
Hmm.
Yeah.
So for our case, we can assume that that is one, and the logic would still be the same.
Yeah. Yeah. The effective will remain same, right? You can keep. I will have to find out though how does like how they actually get the T because that seems like learn temperature parameter. Yeah. Hmm. Okay. Because I didn't find particularly properly like where the T comes from. Okay. Okay. So that should explain what we're doing here in terms of how we train. Post that, the idea is like, okay, how do we use this information? So once you have done this kind of training of your model already, what you can now do is basically create prompts that you want to infer against. So basically, your prompt would roughly look something like that. You have a prompt like, "Is this a cat?" Right, and you pass it through your text encoder, and you get your embeddings. Then you have a cat image. You do the same thing. You get the embeddings, right? So at this point, you can now calculate your cosine uh, similarity loss. Sorry, cosine similarity between these two, right? Or since we're not training it against cosine, you can basically like multiply them and get the same cross entropy calculated against it from the logics that you bring out of it. I just mentioned cosine because it's more standard practice, but yeah, in this case, since we're training it against cross entropy, we're just going to apply the cross entropy on whatever we multiply out of them, and whichever position like gives you the highest rank, like that will give you the information that okay whether they're actually correct or not. Sorry, not the highest rank, but it's just the embedding, so you're going to get one single value out of it, right? So based on this value you can get a confidence that okay if there is a cat in the image or not. Now, how it makes like, how this helps us is that this can now be extended to absolutely anything else. You can ask whether an image has some other detail or not. You can like for example, if tomorrow you want to design a recommender system from scratch, right? And you have no information of what kind of content are people are going to upload, but you do know there are certain kind of content that you would like to promote or give more priority to. Then in that case you can basically have like bunch of priority prompts maybe, right? Bunch of priority prompts listed down, and then basically have your entire system designed to output those items in your corpus which you want to pay attention to, right? Again, this is in a world where your recommender system is starting on a platform that was just created yesterday, right? So at this point you don't have any engagement, you don't know what people want to do. This is a classical cold start issue effectively. So, and this is a common approach used as well these days. Many like some of the fashion startups with which what I have been talking to, they have done this in their own Rexes because they needed to solve their cold start problems, and they basically have been creating these kind of pipelines. So yeah, I mean, this is roughly what Clip does. What I found most interesting in this paper was that like once you like go into this regime of using contrastive loss, you can basically start doing it for everything. Like you can think that okay, I want to create a database of every uh, 3D or geometry or CAD design and CAD designs that are created within a company, right? And then you can like suddenly start like have your entire history of all CAD designs, which were maybe probably documented at some point, annotated like this, and basically train a clip model. And then suddenly you have a database at your hand where you can actually search all relevant CAD designs more easily, right? So yeah, I mean you can basically do it for anything: 3D with music, video, audio. So I'll just share this one in the group after the meet. So basically, I just like use Gemini to get a response of all the things that like different modalities against which clip has been trained, and there have been few works actually. There were a lot of work actually, which out of which one most interesting was actually for me this one from the Google's work that basically combining music, audio, and natural language. Um, so yeah, any questions for far now? Because I'm almost done. We can actually start getting into the code.
So Rajat, could you please repeat that part where you mentioned some of these fashion startups they use Clip to handle their cold
Yeah,
start access?
yeah, sure. Uh, So roughly, for example, suppose they have a catalogs, right? In rec system, it will be rather be called a supply. So basically, they have like items coming in of like different kind of stuff, right? And it can be a red cloth, it can be sleeveless cloth, or etc. etc. Right? And you want to tag them. You want to make sure they're tagged. If the human is not doing the job, then at least if there are buckets that you care about, then at least they should be tagged accordingly. So what you can now do is basically create bunch of prompts like is this a blue shirt, right? Like blue shirt, is this a sleeveless, right? Something like this. You can have like these bunch of prompts. You have your text encoder, pass it and create your bunch of embeddings that you require. So you have your odd embeddings created. Now whenever a supply happens, right, what your system can do is basically take the model, take the images of the item, and basically
Mm-hmm.
your image model will create
Mm-hmm.
an embedding. And now what you can do is then you can basically take your image embeddings and compare against all of these embeddings that you have. The moment you do that, you have bunch of tags created because you know that the tags that you care about. So if you have like 500 tags, that can be a bit of a problem, but then 500 embedding comparison is not a big deal. But the moment you do that, you are able to like get very rich features out of that simple image that you get. And those tagging actually helps going down the line because it no more relies on a human to actually tag that image anymore. Probably you could have used something like Google AI Vertex already provides these kind of APIs, but then you can host something like this very cheap in your own system very quickly. So these kind of pipelines is what I was talking about. You can again like think more in a different regime as well, that okay, suppose I have an image, then you can basically have bunch of prompts that you care about. So for example, if people are doing this one, as in you want to create a search experience for user, right? So one of the candidate generator, so again this comes from like Rex's lingo, the candidate generator is like the first level of filtering that we do over the entire corpus. So what you can do is that okay, you have your images coming in, right? And you basically have a vector db. So once you have them, so like you have your image model, you take the image and you store them in the vector db, and then you have your search query which comes from users, right? You take the search query, you have your text model, and then you turn them into embedding, and then you can do a search on them, search on the vector db itself, right? Vector dbs generally provide a cosine loss, but I'm not sure, like you can basically use canon, and then you can customize it as for yourself. So I just use vector db as a indication that you can use a KNN search here. So this can be another way of doing a candidate generator in a a fashion product, or any kind of clothing product, something like Myntra maybe. Yeah.
Sorry
Okay.
if this is very
So
basic, but what are we training here? We're training the text encoder and the image encoder to work with each other, right?
What are we training here? Right. Okay. Good question. So, okay. In terms of training, now that's up to actually you. If you don't have a text encoder at all at your hand, then in that case, you're going to train both of them. You're going to train both your text and as well as image encoder. You don't have much of an option there, right? So if you look into the clips repository, they are not using any existing weights. They are creating their own text encoder transformer, and then they're training it from scratch. You can
Hmm.
also use an existing one, something like BERT.
Then I'll just set the gradients to 0 for that one.
Yeah, exactly. So when you're like basically you don't like do the gradient update on that at all. So if you're doing it in PyTorch, you don't have to do the gradient update on this model, right? Just do
Hmm.
the gradient updates on this one.
Okay.
Yep.
But for example, if I have both pre-trained text and image encoder, and I'm trying to align their
Hmm.
embedding spaces because they are in a different embedding vector, whatever space. So in that case, I'll have to modify the weights for both, right?
You may, in that case, again, don't modify the text encoder because the assumption is that our text encoder is good enough or should be good
Hmm.
enough. Because if it is not good enough, then I mean, in that case, you don't have any ground truth to actually compare against. So there is one
Right.
particular line in this paper where they actually specifically mention that the text encoders are basically working as weights of a linear classifier. So your weights has to be good enough. So
All right.
if that so that text encoder has to be good enough. What you mentioned here is that you already have an image model at your hand. Yeah, in that case, you can basically transform the final embedding layer. And like maybe probably there will be one embedding, and then you transform into the dimension which matches with this one, and then you do the same thing. However, in this one, you will require like it goes down to the same idea that how much fine tuning will be required for this model. Right? Do you
Right.
actually train it all the layers, some layers? Yeah, that's I guess has to you'll have to figure out when you're doing it. So again, this paper is more about like an architecture idea. Like you can go and do it like this. And I guess a lot of success actually comes from transformer because with transformer you get a better text encoding. Yeah. Without text encoding, I don't see it being like I don't think it's possible because they did reference couple of papers in this I think related work section it was. If you start reading the related section, you will probably get that.
And
And they do
there was
mention
also a recent paper. I think I sent in the group harnessing universal geometry of embeddings. So they were doing something similar. They had an unsupervised approach where they were converting from one text embeddings from one vector space to another
hmm.
without any paired data. I don't know if I think we talked about
Yeah,
it
I
in
remember you shared that. I'll have to probably read
put it
into
in the
it, but
chat.
yeah, it kind of seemed like they're claiming a lot, doing a lot less. But take it. Yeah, I mean, like that's most paper anyway. So, but that's why. But this one, I feel like is claiming not a lot, but
Right.
like it has simplified something and given a good approach, and it
Feasible
works.
things.
The thing is, it works. Yeah.
Feasible to imagine sort of claim.
Uh huh.
I'm saying it's a feasible to imagine claim.
Okay.
We have a question in the chat from Vidushi. Can you talk a little bit about how this can be used in different domains like audio, etc.?
Hmm. Okay. So I don't have much experience with audio, but like provided everything can be thrown at the transformer, I'm going to give some example that I can come up with. Okay. In audio, right? Yeah. Okay. So for audio, it goes down to the same way. So for example, if you're creating the Rexes for maybe Spotify, right? Spotify or YouTube Music, right? In that case, it's the same idea that you have your audio samples created, right? And then you have your audio encoder, which happens to be a transformer here in this case. Right? And I don't think if there are any foundational models for audio encoders like you have for text like BERT or GPT. If there is none, you'll probably have to handle it yourself, but which you can. So your training regime somewhat would look like that. You have your audio sample. Then what you can do here is that you can probably get either annotated text, or if you are YouTube, you probably already have comments maybe, which may not be a great source, but they can still describe it. There will be also annotations of whoever has uploaded this. So what does the song is about, who is it from, etc. Right, these kind of information like maybe the singer, the composer, all these information can be here, right? And then you have a text encoder, right? So yeah, like once you are in this setup, right, after this, like you can basically train it with the same the contrastive laws that we talked about, and we can go back to that vector DB approach. So every time like an uploader or a user basically uploads an audio sample, it goes through your audio encoder, and you stash the embedding that's created into a vector DB. Again, I'm just using the vector DB as an analogy for k nearest neighbor. You can like come up with whatever approach there. But effectively, you're going to do a k nearest neighbor approach. And whenever you have a search query coming in, it goes to a text encoder, and then that embedding gets searched in this vector DB. The same approach. So again, it's very useful for search. If you want something else, again, you don't have much, because this basically essentially solves a problem that when you want to identify if things are similar or not, because it is a contrastive loss in the end of the day, right? What it actually does is that it shows that you need not do classification, you can do classification in a different way. That's one of the things that it actually talks about. So in the approaches section, no, training, there goes evaluation, zero shot being the one of the biggest one that's highlighted here, right? And even in the later part, if you look into the benchmarks, it's all about the zero shot performances. Zero shot as in like you give something to classify of different kind of stuff. Like your same model can classify dog cats, your same model can classify clothes, it can classify ships, it can classify whatever you need. Because it's not classification, it's basically like trying to match a prompt with an image. Because classification is just an outproduct of it, because you are writing a prompt like a classification task, right? Anything else? No, no. Yeah, actually, that paper is about just like claiming about the zero shot performance on classification. So yeah, you can really say that this is basically the kind of paper that solves classification for once and all. But it's any problem that you can think in terms of classification, this is it. Does that explains it? I mean, for the audio one, I mean, the same like would be true for video as well. So like once I share this like set of papers, you can take a look. But like these are the some of the papers that actually do with this. They actually try to do multimodal contrastive learning, where they have video, audio, text, all of them.
I was just thinking, I was wondering about the um, video part itself. So currently, Clip just handles images like static images mapped with
Hmm.
the textual context. But
Yeah.
then if it's video, then we have like different frames, and then we need to basically have a time series, let's say a temporal encoder for it. But then how do we map it with its corresponding text, because it's a single context for a single image, right? Like,
Yeah, I get what you're saying. So I am not like I haven't fully read into how video encoding works in the transformer scape, but I'm going to assume here that basically they have to reduce down the image into a already an existing attention block of some form. So for example, if you have like an image so of 2 cross 22 right? So this is your one single image, and then you have like multiple frames of it. So currently you have like one single image, and that probably gets transformed into a block of maybe 196 multiplied by 768, where 768 is the like the representation size, and 196 is like how I'm compressing it down. Maybe it can be even lesser than that, right? So I guess I understand your question, that you have like bunch of such kind of 196 by 768. So how do I all put them together? Which
yeah.
I think is more of a like how to apply the transformer onto it. I don't have that on top of my head, so I cannot answer that directly. But I'm assuming it should be possible, because once you have like this kind of 196 by 768 representation, then it's a 3D block, and yeah, I'll have to really read of it. Yeah, I cannot even answer that right now. Yeah, I'll have to read how are they actually translating videos.
But yeah, I think it would be an interesting read after going through Clip. How
Yeah,
can it?
yeah. But again, it's not about clip anymore though, because your question is more about that. Okay, how can I encode a video into an embedding? So it's basically about you're trying to answer the question that how do I compress this into a single representation that I can then train the contrastive loss against.
Yeah, true.
This is a, like more of a known entity problem. It's just that I haven't read into it. But yeah, like once you go like understand the clip approach, everything will look kind of like similar-ish in terms of the recipe. So this is more of a recipe suggestion. So yeah. And the entire paper is a recipe suggestion. So yeah.
Yep. Thanks a lot.
Uh, yeah. Any other questions? Maybe we can get to the code then. We see the code is open or not. Okay. Should we like? Is anyone interested to go through the code on like, or do they want to go it on their own? Because whatever I explain, it's the same thing we'll be going through again. So yeah.
If everyone's good with it, I think we can take a look at the code. I mean, for those of us who are doing DL or are planning to do DL at later stages, it'll be easier
Okay.
to like relate.
Okay. Got it. Yeah. I mean, the code can be a bit dense and like time taking, but okay. Oh,
I
yeah,
mean, we'll give
attention.
you a time check at 7:30, but let's try to bring this in so that in the future, if we want to start doing open source or something, we can, use this route.
Okay. Yeah, I mean, like if we start going through the entire model, like be both boring and take time. Because yeah, but what I just wanted to show off is that section where we actually initialize the models and we have both the encoders created. So I was just looking for that one. Yeah. So this is the same section that the paper actually describes, right? So this one that you can take a look, right? So we'll quickly go to the encode image section to find out which one it is. It's the self-dot visual, and wait, initialize parameters, start visual. It's the modified resonate. So you can see, like I was talking about, right, this, right, that in the original code, they basically created their own set of models. So you can see like with the both the vision transformer, sorry, no, this transformer, this is the text one, and sorry, wait, what the hell? Yeah, yeah. Both the transformer and as well as the modified resonate are their own self implementation that they have done. And given it's an image encoder, again it doesn't answer the question of like how the contrastive loss of video will work, but you can see like how the sorry, the forward pass in this case looks like. It's the same one that was shown in the paper code, and that was a good reference for it though. If we go to the modified resonate here, right, this I think has to do with like if somebody knows resonate, for them it will be easier to read. For anyone else, I guess it will be a little bit difficult. There is some modification in the ResNet, which I need to understand like what they have done. There are three stem convolution as opposed to one with an average pool instead of a max pool. So average pool versus max pool makes sense, but three stem convolution, it's something that they have added a bottleneck architecture at the top. Like there's one class at the top. I need to understand why they have done that. I haven't found any good reason for why they've done it or where did they come up with that, but it's there. Uh, Yeah, I mean, like, do we want to go through it line by line? Because I don't have anything to add if we try to do that. So, yeah.
Yeah, I guess, I mean, it's
Yeah.
pretty
Thanks.
self-explanatory code if you don't know
Exactly.
what it
Pretty
wants to learn.
self-explanatory. Yeah, exactly. I just wanted to show the part that where the embedding is created, and basically they're using their own set of implementation and not using already created weights.
How big a resonate is this? Seems pretty small.
It's pretty small actually. It's not that big. Even the transformer one. Let me find it. The transformer open over.
It's just like four
Uh,
layers of fibers.
yeah. This is resolution transformer, vision transformer. Yeah. Vision transformer. The forward is this. Permute, torch, cat, length, permute. Oh, wait. This is just the encoder, is it?
This is the transform VIT.
This is the. Yeah. I'm just looking for is it the transformer only or is it like the concatenation of it as well? It doesn't seems like the concatenation. No, definitely not. No, wait.
No, but
Context
why would
length.
they use VIT if there's a resonate involved?
Sorry.
Why would they use VIT if there's a resonate involved?
No, they actually have it as an option. Like use whichever
That's
you
it.
need. Yeah. They basically have multiple weights published for it. So yeah. I guess even in the paper they actually tried to establish the same thing, that you can use this approach even with the older kind of image encoder that were available, and it will still work the same. I guess VIT did perform a little bit better, but yeah. So like coming back to your question, that if you already have a trained model, yeah, you can do that. Because even they are saying that you can do it. You should do it. This point. So yeah. Yeah. Because and I can see some questions. I've missed all of them though. I think even something simple as layer of a whisper can be used in club approach. I haven't read Whisper's person idea. It's pretty user transcription. Nice question. I guess the answer to the video encoding would have an additional time dimension in the simulator. Course. Yeah, I'm not sure if having the time dimension would be really helpful here, especially because the two parts of it here, right? That how do you really want to actually ground your video against the text? So one is you have a huge, large text, a description of maybe an 8-second video, and then you ground both of them together under a single embedding, or you actually ground them, by context, that okay, I'm going to break it down at 1 second level, and each for 1 second I'll have a separate chunk of description, which, yeah, I'm not sure if having a time dimension there would be really helpful, but yeah, I'll probably have to do that. Because I'll stop sharing. Mikhail, I think you can stop recording now.